if you are watching this, it's very important that you go all the way through it because there is a couple of exciting things that I worked out and only took about 5 or 6 lines of code. First of all, this is graphics, and you may or may not have much experience in graphics, but there's this book. Now, it was done in 1986 by Lee Amarel. I probably slaughtered the name, from the Netherlands. And he wrote this book, Programming Principles in Computer Graphics. And I've had the book for a long, long time, but I haven't had any time to work on it. And I'm going to do so now since I've got the software in place to do it. This, like I say, is done in 1986. I checked at John Wiley. They don't have it at all. But I did check at Abe Books, and you're going to have to check any used bookstores and see if you can find a copy, or search the internet for all the usual places. But the book, he starts off and he says here somewhere that all you need is some graphic software to display the results. And the thing is, he uses a couple of functions. Move, I don't know if I can highlight. Yes, it will highlight, but not very well. There's the move and the draw, and we have those from the DXY to PS. And so what you do is you write a function, call it move, another one called draw, and you just print the M and the D lines with the X and Y coordinates, and you can reproduce this program. Now this program here is called squares, and it produces this figure here, and it's just squares. I think there's 50 of them. How many does he do? He does 50 of them. There are 50 squares. Starts out with the big one that's 8 by 8, and then as it decreases in size, he rotates it whatever the arc cosine of 95 is. Let's see, 0.95. I got my calculator here. Can't read it because I don't have any lights. Let's see here. Arc inverse cosine. Something like 18 degrees. Don't quote me on that. So I did the following. The program's called squares. There go y'all get to see all my typos. And you can see here that I typed it in. And I added the functions move, which does a printf, M, and then the X and Y values. And I also did one other thing. I made a global variable here. I know that's bad programming practice, but did a scale by 300 because the dimensions that the squares program produces is so small, I had to multiply it by a large value to get it to generate an image that's a good size. Did the same thing for draw. You just printf D, scale X and Y, and then I have the home, and then for the pen, I want to change pen sizes just to experiment. And I have a shell run.sh. What I do here is I compile it, execute it, output to the file squares.dxy because it generates the AMDEC DXY graphics language. Then I can convert it to PostScript using our little DXY to PS program that I've got going, and generates a PostScript image, and then I can display it. Now there are two other programs that I did, Quadrant 1 and Quadrant 2. In the book, right after he does this, goes on to the next chapter, shows you how to do rotations, and then he has a little program here that has a little arrow, and it starts here and it goes around, I think 14 times, whereas, yeah, there's 14 times, and this is the output you get. Again, all you need is the move and draw functions. So I did it twice, and I'll show you why I did it twice. First of all, let's look at my output from the squares program. And you see that it generates the same figure that he's got. Now, either events, I know it's not PostScript, but events on display starts aliasing these lines. And if I magnify them, you can see that most of them are pretty well done, except for the small angles relative to the horizontal and vertical. This is kind of the effect that I was talking about that you would get with a mechanical plotter, but it's a very nice image for the quadrant or the arrows. I guess I can show you the code here. Whoops, no, I don't want to, I want to look at it. I don't want to edit it. Generates the same thing he does. And if you can possibly find a copy of the book, it's worth your time to work through it and then do these little examples. One of the things, if you do it on Quadrant 1, you'll see here this arrow is not quite vertical, and the one here is not quite horizontal. And I ask you to modify the program so that this one comes out vertical and this one comes out horizontal. All right, I did the following. You remember that I added color. So I take the same program, all right, but I do the following. I set 3 variables RGB. These are going to be my RGB values. And where did I set? Oh, here. I start out here for each one of the arrows. I set the R value equal to 1 minus I, which starts at 1. Actually, he should have started at 0, but that's all right. I set R to 1 minus, and I set B to I over 14. So this will start out with a red arrow, and then when I is 14 for the last arrow, this will be 1. 1 minus 1 is 0, so the red component will be 0, but the blue will be 1. So this starts with red and goes to blue for each arrow. If I look at the output, you can see, starts out with red. I modified the arrow a little bit, just experimenting. And as we go around here, halfway this becomes magenta, and then it turns to blue for the last arrow. So my little modification to the DXY to PostScript routine to add color opens up all kinds of avenues for graphs. Now, I told you on DXY to PS that I hadn't spent any time at all on solving the hatch problem? Well, I guess I had a dream or whatever, and I solved the problem, and it only took 2 lines of code. Now, because of that, I did the following. Instead of doing hatching, I just said, why not just fill it with a color? And that's what I did. And you added one line to do fill, which is a PostScript command to, on the last connecting or enclosed figure, fill the inside with the color. So this kind of effectively does what we saw in the videos if you looked at them for plotters on YouTube. Now here's what I did. First of all, let me show you this. This is a diagram of the RK3588, which is the SoC in the Orange Pi 5 Plus. And you can see that it's very complicated. I have no idea how many transistors are in this puppy. I'm guessing close to 1 billion, but it's just astronomical. So looking at this diagram, I'm saying to myself, now that I can draw rectangles or any enclosed polygon, I can fill it with colors. And I'm thinking, how long would it take me to reproduce this? And I did it in less than 45 minutes. You want to see my results? This is why you should stay. Here it is. I was able to reproduce the figure. Didn't get the exact colors, but I don't care about the colors, and they didn't either. So this is the architecture of the RK3588 reproduced here in all its gory detail. And I don't think I have any typos here, but that's an exercise for you to find. Also, you'll note one other thing. I created a alphabet. I've got that. I think I have it right here, don't I? Let's see here. Did I do it? What did I call it? Where is my test plot? And my little routine to do graphics is called FormGen. Test 1, test 2. Oh, here it is. This is a demo of my alphabet. Lowercase. You want to see these in magnified form, we can do that. Let's go to 100% here, maybe even better, more. So here are my lowercase letters. I'm not particularly fond of the A. I guess I could up it a little bit, but I just tried to keep, this is a problem I have from 2 years of kindergarten because my birthday is on the September 26th, but I was in kindergarten 2 years. And then when I was a freshman in high school, we learned penmanship, and we used a Big Chief writing tablet. I don't know if you remember those. It's a little line thing. You have like notebook paper, but there's a dash line halfway in between, and lowercase lowercase letters have to stay below that line. So, okay. Then here's all the caps, and I have some special symbols. I didn't print them all out here. I also worked out how to do arrows, and then for later seminars, I'll show data buses this way instead of showing every one of the lines. Like if you had an 8-bit processor, you got an 8-bit data bus, bidirectional. You have data lines D0 through D7. Instead of doing them this way, you just do it with one line with a bar through it to show that that's multiple paths or multiple connectors. And you can put a number above this thing to show how many there are. So 8. One of the things in the RK3588 is you got 64-bit data buses. You have 64-bit instruction buses. So you do not want to draw every one of those lines. And I think on the bottom of the chip, they're little pinpoints of connections, and there's over 1,000 connections. Here was my test to see about filling in rectangles. So I filled in this rectangle with red. Then I drew another rectangle internally, made its color white. Then I put text in the middle. And I have a choice on drawing rectangles in the similar fashion you saw on hatching, that you could do it with just the rectangle with no border, or this would be the case for the white rectangle, or you can do a rectangle with the hatching and the border. And then of course I can just draw the rectangle. So as another demo, what did I, oh, wait, did I discuss everything? Whoops. On my little character set, you can see that I can change the color, and I spent extra time doing the rotation so that I can draw the text at any angle. In DXY2PS, the PostScript fonts can only be done at 0, 90, 180, and 270, but I can do them at any angle. I just demonstrate these three. And I took one that was non-45, two that were multiples of 45. So that opens up a lot of stuff there. What was let me look at my second test program here. This was it, okay. So that was the exciting things that happened since we last talked. And this opens up a lot of avenues, a lot of work that can be done in demonstrating things for the Orange Pi, and I plan on doing that. And I even have some uses for this in research. So I'm excited. Now, yes, there are packages that can possibly do this, but I'm a fan of typing. So this is like the DXYGL. I have to, I type in things, but I can put things wherever I want. And if I don't like the placement of something, I can shift it, 1 or 2 pixels or any distance that I want. So I think I got everything covered. I hope that you can see that this is actually a better technique to fill with the color than with the hatching. See, for the hatching, I only had 1, 2, 3, 4 options. Here, if I fill with the colors can go 256 by 256 by 256 in RGB. So that's where you get your 17 million and whatever follows that. So that's 2 to the 24th options. By the way, your monitor can generate 17 million colors, but some tests were done on human subjects before the EPA or OSHA started generating paperwork, but experiments were done for human beings to figure out how their eye responds to color. And even though there's 17 million colors you can generate, the human eye that hasn't suffered from any diseases and your physiology hasn't suffered from any chemical imbalance, human eye can only recognize about 101,000 colors. In fact, I can test response of my own eye by using, I'll come back. I can use this program. I can generate two squares, and I can set the RGB value in one square to one value, and then change it by just one or two values, you know, a fraction of a percent, to see how far or how large a change has to be made before I can tell the difference. It's kind of like those, you know, color blindness tests. Okay, I am through. I have exhausted my voice. Trying to think what's next. I want to go off and figure out where we were going when I got sidetracked on graphics. And by the way, on this book, since I'm going through it, maybe you'd be interested in going through it also if we can find copies of it. So go search to see if you got copies. And I need a whole bunch of people that are interested, and I need a whole bunch of likes on this video. Otherwise, I feel like I'm wasting my time. Thank you very much for yours. Hope I haven't wasted your time. And I finally got something done that I was been putting off for decades. Thank you.